Okay, welcome back. This is the start of Unit 2, or at least one of them. Let me share my screen and we'll get right into the fluid mosaic model. Let's see here. Here, screen sharing, Zoom. Okay, so we are starting to talk about the plasma membrane. And for the plasma membrane, the model that we follow for how we describe the plasma membrane is called the fluid mosaic model, right? This was proposed by Singer and Nicholson back in 1972 rather. And the model says that when you're kind of looking down on the plasma membrane, it kind of looks like a mosaic, right? Like, you know, mosaics with all those glass pieces. And the fluid mosaic model says that there are proteins embedded in a phospholipid bilayer. So again, here is our phospholipid bilayer. Again, we have, remember, hydrophobic tails with our polar hydrophilic heads facing both the inside and the outside of the cell, because those are both watery environments. However, those tails, which are nonpolar, hide away because they do not like interacting with water. All right, so what you can see is within this phospholipid bilayer, you also see these big purple blobs, right? And those big purple blobs are proteins, all right? So those proteins basically kind of float throughout this phospholipid bilayer. And it's really important that this phospholipid bilayer is fluid, all right? So the phospholipid bilayer is very fluid. It is dynamic. It moves around. So then if you could have a microscope powerful enough to look at these individual phospholipids, what you would see is that there's constant motion, right? There's very fluid. And those proteins are kind of floating around inside of there. Again, the phospholipid bilayer, this is one of the formations that forms spontaneously in water when you just stick in your little phospholipids. Another thing that forms spontaneously that we mentioned before is a structure like this, right? That's called a micelle. Maybe it's with a Y, micelle. I'm not sure. A micelle. That's not as important as this, which is the phospholipid bilayer. So remember, if we zoom in on the phospholipid bilayer, we have a watery internal environment and a watery external environment, meaning the heads, the polar heads, are always going to face both inside and outside. When we zoom in, what you can see is that we have those, again, non-polar hydrophobic tails, which are, again, a lot of methyls, very hydrophobic. And then you have those polar heads facing both internal and external. And if you zoom in on a phospholipid, as we mentioned before, those are amphipathic. Amphipathic, meaning they have both a polar and a non-polar aspect to them. The polar, what you have to know is that they have a phosphate group. Remember, the backbone is this glycerol molecule, and then you have these two non-polar tails, right? One of them usually is unsaturated with a kink, with a double bond, and the other is usually fully saturated. Those are in animal membranes most of the time. If you zoom in and you look at all of the different components of the plasma membrane, there are several that you have to know about, right? So the first is the phospholipid bilayer itself. That is what creates the kind of selectively permeable barrier. Then we have membrane proteins. Remember those blobs that are floating around. Then we have glycoproteins, glycolipids, and cholesterol, right? So I tried to give you a nice kind of picture here of all of the different components. We have the cytoplasm here on the inside, which is a watery environment. We have the extracellular environment here, which is watery. Then we have several different types of membrane proteins kind of floating around. We can have membrane proteins that are only on the surface, like this. You can have membrane proteins that touch the hydrophobic tails. You can have membrane proteins that go all the way across the plasma membrane. We also will see glycoproteins. The way to identify a glycoprotein is that they have these carbohydrates attached, right? So you can see those kind of carbohydrates attached here, right? Then we also have what are called phospholipids. A glycolipid rather, where the lipid itself have these carbohydrates, right? So the phospholipids themselves have been modified with carbohydrates. And then lastly, we have cholesterol, which you can see embedded within, they kind of intercalate or insert themselves within the hydrophobic tails. So let's go through each of those. But I just want to remind you first about our kind of membrane fluidity. So membrane fluidity depends on fatty acid saturation, right? The more unsaturated your tails are, meaning the more kinky, right? So increased unsaturated, meaning you're going to increase kinks, meaning you're going to increase the fluidity of the membrane, meaning it's going to be more fluid. They're not packed in as tightly. If you increase the saturated amount of phospholipids, you are going to increase the amount of hydrogens on them, right? You're going to decrease the amount of kinks or double bonds, and you are going to decrease the fluidity, right, of that. So this would be more likely to be a kind of solid, which would be very, very bad, right? We don't want our phospholipids to solidify, otherwise that cell cannot live. Right, so membranes rich in unsaturated fatty acids are more fluid than those with saturated. And the way, again, I remember that, Arctic animals are very kinky, oil, more kinks than fats, right, which are solid at room temp. All right, so fluid mosaic model. So membranes, again, are fluid, and all of their components are dynamically in motion all of the time. If they solidify, that cell can no longer live, because membrane fluidity is really important for transport, for communication, for a lot of things, right? These amphipathic phospholipids, and again, amphipathic meaning we have polar head and a non-polar tails. They form this word, which if you ever have to describe a plasma membrane on a test or on an AP test or in my test, the phospholipids form the selectively permeable membrane, meaning some things can get through, other things can't, right? So here is just kind of a molecular drawing of those phospholipids. Remember, those heads are interacting with the water through what? How are they interacting with the water? Well, they're interacting through hydrogen bonds. Great. And then these nonpolar tails form a barrier. I always think of this kind of the nonpolar tails here as being the blockade. Like nothing's getting through unless, nothing's getting through unless you are small, uncharged molecule. So for example, the things that we're going to talk about that can diffuse right through the plasma membrane with no problem, meaning they can get through this kind of nonpolar blockade, are the gases. So we're going to see oxygen, we're going to see carbon dioxide, we're going to talk about nitric oxide at some point as well, and the steroids. Remember, steroids are a lipid composed of 4 carbon rings, right? Those can diffuse right through. So they're going to go from an area of high concentration, and they're just going to go right through the plasma membrane down to a lower concentration, right? So that's why this membrane is selectively permeable. These things get right through. Small uncharged molecules can get right through. However, larger charged polar molecules cannot get through. This acts as, the nonpolar tails acts as a barrier, and the polar things cannot get through. So if you are polar or charged, you can't get through the plasma membrane alone. You can't just diffuse. So what you need are proteins, right? So here are these membrane proteins, which are going to be really important to help act as a gatekeeper to get these polar charged molecules through, right? And they can get through different ways, as we're going to see later. So here we have a channel where things can get through. Here we have a protein that needs to use energy, and we'll talk about that as we get through. All right, so what about water? Water is small. Do you think it could get right through the plasma membrane? So what do you think? So what do we know about water? We know that water is polar, meaning it has a partial negative and partial positive charges. So what that means is that this water is not going to be able to diffuse right through the plasma membrane, right? So we have these special type of membrane proteins called aquaporins, right? So aquaporin, and that is a really good name for me because aqua means water, porin means like a pore or a channel, right? So this is a membrane protein that is embedded in the plasma membrane. It has a channel or kind of a hole through it where water can get through plasma membranes. All right, so here is an aquaporin where water, which is, polar, small, partially charged, and water can slip right through, both inside and it can go in both directions, right through the plasma membrane, through these aquaporins, right? So aquaporin is a transmembrane protein, meaning it's a protein that spans the plasma membrane, goes all the way across the plasma membrane, and it allows water to go through the plasma membrane. All right, so if we look more carefully at all the different kinds of proteins that are in the plasma membrane, I want to point out a couple, and this can get really confusing for people, but I'm going to try to make it as simple as possible. So the first kind are peripheral membrane proteins. These are proteins that are bound to the surface of the membrane. And for me, what that means is that they never touch those nonpolar hydrophobic tails, right? So here is an example of a peripheral membrane protein. Here is another example of a peripheral membrane protein. It's not touching those hydrophobic tails, right? The second kind is called an integral membrane protein. These are plasma membrane proteins that somehow touch the hydrophobic tails, right? So this is an integral membrane protein, as is this, as is this, as is this, all right? Some integral membrane proteins are called transmembrane, meaning that they span the entire plasma membrane, right? So this guy in green is a transmembrane, and this big purple guy. Those are both transmembrane proteins. They're also called integral membrane proteins, but a more specific name is a transmembrane protein. All right, so hydrophobic regions, so let me rephrase, we're gonna go over here. So hydrophobic regions of an integral membrane protein, remember integral membrane protein is that they're gonna touch those nonpolar tails. They have nonpolar amino acids that are going to face those tail regions. So what I mean by that is that the R groups that are interacting with those nonpolar tails, guess what? Those R groups better be non-polar in nature in order to interact with those tails. However, the R groups of those amino acids that make up the protein that are interacting with the polar regions, those guys better be polar, right? So hopefully that makes sense, that as a protein folds, for example, where it spans the membrane, so here we have that secondary structure of an alpha helix. When that alpha helix folds, all the regions pointing out towards the nonpolar tails are going to have nonpolar R groups. Whereas out here and over here, you're going to have those polar R groups. Okay, so how can proteins span the membrane if the membrane is amphipathic, meaning it has both hydrophobic and hydrophilic regions? So we just kind of talked about this, where this region of the protein, any region of that membrane protein that is interacting with those nonpolar tails are going to have nonpolar R groups that are sticking out and interacting with those tails. So there's going to be nonpolar R groups there, right? However, any region here and here, any region touching the polar tails, the polar heads are going to have polar R groups, right? So those are all going to be polar, right? So again, the hydrophilic R groups are going to be exposed to the watery or aqueous environment, whereas the hydrophobic R groups in this protein are going to be interacting with that hydrophobic tail or the core of the phospholipid bilayer. All right, so the other two other things that are in the plasma membrane, one are glycoproteins. These are proteins. So again, proteins are amino acids held together by peptide bonds. They have an amino end and a carboxyl end. And they have those 4 levels of protein folding. So these glycoproteins have carbohydrates or sugars attached to them. So if we look here, this here is a glycoprotein. This is a glycoprotein. This guy is a glycoprotein, right? And you can tell because it's got these kind of regions. And if you blow up those regions, what you can see is that each of those is made of monosaccharides that have come together to make, this guy has 1, 2, 3, 4, 5, 6, 7. So to make a polysaccharide, which is bound to a protein, right? So those are glycoproteins. They're really important for cell-cell interactions. And one of the things we're going to talk about later in the class is glycoproteins are important in giving our blood type. So for example, the A, B, O blood types, those are dictated by glycoproteins. All right, glycolipids, on the other hand, are lipids that have carbohydrates bound to them. So instead of being a carbohydrate bound to a protein, these are carbohydrates or sugars bound to lipids. So here they're shown in yellow, where we have lipids. Here's a good picture of one down here. A lipid that has been modified or have sugars attached to them. All right, and what we're going to see is that is really important in cell signaling, in trying to communicate with other cells. So we'll call that cell communication. All right, so glycoproteins, proteins modified by carbohydrates, important in cell-to-cell interactions. Glycolipids are lipids or phospholipids that have been modified or have carbohydrates attached to them, and they're important for cell signaling. All right, so the last main component of the plasma membrane is something that's really important, and you've seen it before. It's cholesterol, right? And you always hear cholesterol is really bad, right? you have too high cholesterol. And that's not 100% true. So yes, high cholesterol can be very, very bad for some of your cardiovascular functions. However, cholesterol is an absolutely essential part of the plasma membrane. So if you look at cholesterol, it is, again, primarily nonpolar. So all of this region here is nonpolar. If you look carefully, you do see this little hydroxyl functional group, which is polar. But the most of it is nonpolar. And so cholesterol is a steroid. Remember, it has those 4 carbon rings. 1, 2, 3, 4 carbon rings. It is a lipid. It's categorized as a lipid. More specifically, it's a steroid. And this interacts with those nonpolar tails. So cholesterol inserts itself into the plasma membrane. If you look here, we see our 1, 2, 3, 4 carbon rings. Notice that we have a region of cholesterol that is interacting with those polar heads. And if you had to zoom in on that, it's going to be the OH, or the hydroxyl group, that is actually interacting with those polar heads, because that's the only part that's polar. The rest of it kind of lays into these and interacts with those nonpolar tails, right? And it has 2 different roles depending on the temperature of the organism. So the first one is that the first one is at high temp. So at very, very high temperature, what happens is that the fluidity of the plasma membrane is way, way up, right? It's a very, very high fluidity. And what can happen is if it gets too hot and too fluid, the plasma membrane and those lipids can actually have so much kinetic energy that they can pop away from each other. Not pop, but they can fall apart. So what happens is that cholesterol is like glue, and it kind of holds them together. It kind of makes interactions here where those nonpolar tails are not going to fall apart from each other, but they're going to stay close. In cold temperatures, we already know that in cold temperatures, you're going to have increased unsaturated, meaning more kinks. Another thing that cholesterol does, however, is that in low temperatures, we know that you get decreased fluidity of the plasma membrane, right? And we also know that if things are less fluid, then the nonpolar tails like to pack in tightly, right? So what the cholesterol does is that it actually prevents tails getting packed into one another, packed really, really tightly, therefore making it increased fluidity, right? So at low temperatures, cholesterol prevents packing to increase fluidity. At really high temperatures, cholesterol acts like glue in order to keep the membrane together. All right, so here's a piece of homework. I will post this as an assignment when and if I say it's due, but this is just that would be a nice reference for you, is to draw the plasma membrane, including all of the components, and make a key describing their functions. I also want to point out at the end of my PowerPoints, I have practice questions, right? When I post the PowerPoint, these answers are down here in the presenter notes. Presenter notes. So that you can always go back and get them. All right, and that's it. Let me stop.